It gives me great pleasure to welcome both Edward Cawthorn, who is Secretary of the Friends of the Union Chain Bridge. He will talk about the history of the bridge and its designers. And then Simon Rudman, Design Manager at Northumberland County Council, will describe aspects of the execution of the project for its restoration, completed very recently. And then if time permits, I gather there might be a short time-lapse video at the end of our session.
Thank you very much, Chairman, for that welcome, and thank you, ladies and gentlemen, for inviting me here tonight to talk about the Union Chain Bridge and its remarkable designer and engineer. I normally talk about in these talk, and I'm calling it a talk rather than a lecture because I wouldn't presume to lecture on it. But anyway, I hope that it's sufficient for your purposes. Normally in my talks, I also cover the restoration of 2020 to 2023. But I'm very pleased that Simon is here tonight to talk about that element of the history of the Union Chain Bridge, which is in itself a very fascinating one. So this, yes, is a brief overview of the history of the Union Chain Bridge and of Samuel Brown, Captain Sir Samuel Brown of the Royal Navy, its designer and engineer. Yeah, in his history of bridge, I beg your pardon, there we are, yes, I'm looking at the following. In his companion guide to Northumbria, Edward Grierson in 1976 said that the Tweed is a beautiful river throughout its length, and the scene at Union Bridge is nothing less than idyllic, and so it is. And I assume that most of you have visited the Union Bridge at some time, but perhaps not. I mean, it is a hidden gem. It is a Guinness World Record holder, as you probably know. And you probably also know that within this region, we have the world's oldest vehicular suspension bridge, or at least half of it, because the other half of it is across the border in Scotland. But there we are. I mean, it's a remarkable world record to hold the world's oldest vehicular suspension bridge down two relatively minor country roads in North Northumberland and Scotland. It's a forgotten gem, so forgotten, in fact, that in his definitive history of bridge engineering, published in 1911, H.G. Tyrrell said that the Union Bridge was blown down in a gale only 6 months after it was completed. Well, we know that it wasn't. We know that it survived for 200 years, and following the recent restoration is likely to survive for another 200 years. But that calumny probably originated from the blowing down of the suspension bridge, a pedestrian suspension bridge further up the River Tweed at Dryborough in 1817. I think that's where Mr. Tyrrell got his lines crossed. The suspension bridge at Dryborough was designed and built by a local blacksmith in Melrose called Smith for the Earl of Buchan. And Mr. Smith put the unfortunate blowing down of the suspension bridge, he attributed that to a tornado, which of course are quite prevalent in the borders. But anyway, poor chap, it must have been an embarrassment for him. And Dryborough Bridge was replaced after that. But I think that's what Mr. Tyrrell must have been thinking of. But anyway, that calumny was repeated in 1970 by David McCulloch, who wrote a very thorough work on the Great Bridge, the Brooklyn Bridge, and the Roebling family who built it, who designed and built it. And Mr. McCulloch obviously didn't think very much of Captain Brown, because he devotes about 3 lines to him in his book, and says, as you'll see, Brown's suspension bridges came down about as fast as he put them up, one after another, at Berwick, Brighton, Montrose and Durham. Well, we know that the one at Berwick that he's thinking of is Mr. Tyrrell's mistake. At Brighton, he must be thinking of the chain pier that Samuel Brown successfully designed at Brighton, and it operated very successfully for some 70 years or so as a pleasure pier and also as a pier for steamers going across to France. But it did blow down in a terrific storm. At Montrose, the suspension bridge there lasted a full life and was only replaced when it came to the end of its useful life by a masonry bridge. And at Durham, I'm supposing that all he could be thinking of was an ill-fated design of Brown's for a railway suspension bridge, if you can imagine it, as an extension to the Darlington and Stockton Railway. And I think we would all agree that putting a railway line over a flexing suspension bridge is probably not a good idea. But anyway, that's what I think Mr. McCulloch must have been thinking of. But it was quite unkind of him to say that Brown's suspension bridges came down as fast as he put them up. There's the Brighton pier the day after the storms blew it down. And a similar pier that Brown built, the Trinity Pier at Newhaven on the Firth of Forth, lasted as long as the Brighton Pier. And again, in a very severe storm, it sadly blew down. But there are remnants of the pier house, etc., still at Newhaven. So why did we need to build a suspension bridge in that remote part of North Northumberland, or North Durham as it then was? Well, towards the end of the 18th century, there was an increasing need in Berwickshire, in the Berwickshire Merse, for coal and lime especially for the agricultural parts of the Merse, from the pits and lime works of North Durham, because you remember at that time, what is now North Northumberland, the ancient areas of Norhamshire and Islandshire formed part of the detached enclave of County Durham known as North Durham, as did the Farne Islands and Monk's House, that you will know, between Bamborough and Sea Houses, where the monks landed from the Farne Islands. It itself, strangely, was a part of County Durham, a detached part. So we're talking about, in this case, about taking lime and coal from the pits and lime works of North Durham to Berwickshire, which didn't have any resources like that. And we tend to forget these days about just how much of a barrier a river can be, or certainly was in those days. If we look at the map of the time, there is where the chain bridge now is, and where a ford existed to take commodities across into Berwickshire and vice versa. There's another ford called the Market Ford, just on the border of England and Scotland, which was also used from time to time. But the nearest bridge was at Berwick, now called the Old Bridge at Berwick, or off this map down at Coldstream, because Norham Bridge, the masonry bridge at Norham, wasn't in existence at that time. And so any trip carting lime and coal from North Durham across into Berwickshire had to be very carefully planned and would take some considerable time. Or you could subject yourself or tackle the ford at New Waterford. The yellow arrow points to it, which was responsible for deaths to both livestock and occasionally humans during periods of flood. It was known locally as the Ford Precarious, and precarious it certainly was. But this was an ancient strategic, just to digress slightly, an ancient strategic area. And in this map by Wenceslas Hollis of King Charles's camp or Liga at Horncliffe in 1630, we see that the first arrow there points to where the bridge now is, and the second is to the Ford Precarious, the new water ford known or marked on Hollis's map as the King's Ford. So it was a ford in those days as well, and it's obviously quite an ancient crossing point. Let's introduce ourselves now to Captain Sir Samuel Brown of the Royal Navy, and this is the only known portrait of Samuel Brown. It's owned by the Royal Pavilion and Museums at Brighton and Hove, probably because of his, well, almost certainly because of his design of the Brighton Pier, where he is held in high esteem, as he is in Berwick and Horncliffe and Paxton. He spent all his career in the Royal Navy before he moved into in his retirement into the manufacture of chains. He served for the most part in the Newfoundland and North Sea stations, and very soon developed an interest in improving the rigging of Her Majesty's ships by replacing hempen rigging with iron chains. And he patented a design of open chain links for rigging and other purposes, and actually persuaded the Admiralty to allow him to test this his ideas on HMS Penelope in 1806. He retired in the rank of commander and became an honorary captain later in life in 1842. There's a picture of one of the ships on which he served. He would have known Hornblower if Hornblower had been a real person, because that's the sort of period we're talking about. And there's HMS Phoenix in action against a French frigate. HMS Phoenix, one of the ships on which Brown served. And in this picture of the bombardment of Algiers, with HMS Impregnable in the foreground, you'll see hempen rigging coming out of one of the horse holes, and on the other side, iron chains, iron rigging coming out of another horse hole. So this was in a period of transition between the exclusive use of hempen rigging and the newfangled iron rigging that was being introduced as a result of Brown's patents. And so convinced were the Admiralty of the success of iron rigging that Brown became an exclusive supplier to the Admiralty, and his firm Brown Lennox were exclusive suppliers right through until the early 20th century. Brown originally set up his chain works at Millwall, the Isle of Dogs on the River Thames. But in partnership with his cousin Samuel Lennox, he also opened a chain works at Pontypridd, and it was from the Pontypridd chain works that the iron bars and other iron work for the Union Chain Bridge was produced. The Pontypridd chain works of Brown Lennox survived until the early part of this century, actually, and were demolished to form I think a Sainsbury's supermarket. But they were a very important part of the British chain making industry. And there we have what we call an iconic picture, I suppose, of Isambard Kingdom Brunel, standing in front of the chains for the SS Great Eastern, forged by Brown Lennox. And it's chains of that sort, formed of elliptical chains, that the Duke of Gloucester thought he was going to see when he came to visit the Union Bridge shortly before the restoration started. He expressed surprise that the Union Bridge wasn't formed of these what we would all imagine would be traditional chains of the elliptical design, rather than chains formed by joining 15-foot iron bars together. In 1817, Brown took out a patent for specification for the construction of iron bridges of suspension, as he called them, it's on this specification that the Union Bridge was eventually built. But some 15 years before that, the Berwick and North Durham Turnpike trustees had taken out an act in Parliament enabling the trustees of the Berwick and North Durham Turnpike Trust to construct a crossing of the River Tweed between the parishes of Horncliffe in North Durham and Hutton in the county of Berwickshire. And so that act was in force from 1802, but the trustees did nothing for almost 20 years to act upon it. But they were considering the alternatives for the crossing to replace the Ford Precarious at Newwater Ford. And of course the alternatives were a traditional masonry bridge, which would have taken a long time to build and cost a lot, and then this revolutionary design that was put to them by Captain Brown, who had local connections. He was connected to the Humes at Paxton House and the Milne Humes at Milne Graden further up the River Tweed, and may well have served with Admiral Milne Hume in the Royal Navy. But Brown presented to the trustees this extraordinary design, this revolutionary design for an iron bridge of suspension that would carry vehicles, something that had never been done before. And the trustees, amazingly, took a great leap of faith by contracting with Brown to build this bridge. It could have been a disaster, and it could have cost them a lot of money, but they put their faith in Brown and entered into a contract with him to build this bridge between Horncliffe on the English side and Hutton or Fishick on the Scottish side. The original location for the bridge was, as shown on the left-hand arrow there, actually following the course of the Newwater Ford, which the bridge was to replace. But fortuitously, just before they committed themselves to building a bridge in that location, there was a very significant flood in the River Tweed, which persuaded both Brown and the Turnpike trustees that if the bridge were to be built there, or if it had been built there, it would have been inundated by the flood and washed away. So they took the decision to move the location of the bridge upstream from Newwater Ford to where the right-hand arrow is, and where, of course, the bridge is now built. And they raised the ground, they raised the level of the ground by 60. It was already higher, but they raised it so that it was about 16 feet above the proposed location at Newwater Ford. And that was sufficient to ensure that the bridge was above normal flood waters. Whether you can read that properly, the height of the bridge platform above normal summer water is 27 feet. So quite a comfortable gap between the river and the decking of the bridge. The height of the platform above the biggest known flood in 1820 was 10 feet, which was probably sufficient. But in 1948, the height of the platform above the flood waters was as small as six feet, which was pretty precarious. And there we have a picture of the bridge in 1848 at the height of the very severe flooding in eastern Berwickshire and North Northumberland. And apparently, if you were brave enough to stand in the middle of the bridge at that time, you could have touched the water with a walking stick. So the decision of the trustees to build the bridge in that location was absolutely vindicated, and the bridge has survived in that location to the present time. Let's just have a look at the timeline for the construction of the bridge. We'll remember the Parliamentary Enabling Act in 1802. In 1817, you saw the patent that Brown had taken out 15 years after the Enabling Act. And in 1819, the contract was let by the Turnpike trustees to Brown based on his drawings of September 1818, which themselves were based on the patent, the detailed patent that he had taken out. On August the 2nd in 1819, the foundation stone was laid by the chairman of the Turnpike Trust, William Mole, and remarkably and extraordinarily, less than a year later, the completed Union Bridge was opened by Lord Hume. So I mean, it was built from scratch in less than a year. And this photograph was taken this morning. This morning, in fact, at the Union Bridge. It's a commemorative stone commemorating the original foundation stone that was laid by William Mole in 1819, and that stone was cemented into place this morning, and you'll see that looking up from the stone, you can actually get a good view of the bridge itself. The first foundation stone laid by William Mole on the 26th of July 1819 contained a time capsule of those days with various artifacts and some money. And on the night of the laying of the foundation stone, the time capsule disappeared and has never been recovered, as the Berwick Advertiser reported. Brown would not, I think, claim to have been a bridge engineer first and foremost. He was a chain engineer, and he developed chains and looked for ways in which chains could be used, apart from the very successful use of chains by the Royal Navy. And I think it's noteworthy that in all his bridge engineering and pier engineering, he had the assistance of civil engineers. And in the case of the Union Bridge, he took the advice of John Rennie, the Scottish engineer. In preparing a proposal for the Clifton Suspension Bridge over the Avon Gorge, he teamed up with Charles Stewart Drury, an engineer. He didn't win the contract for the design of the Clifton Suspension Bridge. He was second choice. Our patron, Professor Roland Paxton, having studied the designs carefully, is convinced that it would have been, had he won, it would have been a good choice, and it would have been a successful contract. But Drury assisted Samuel Brown in preparing those drawings and the proposal for the Clifton Suspension Bridge. And he also produced a monograph dedicated to Samuel Brown about suspension bridges, including the Menai Bridge, Berwick Bridge, Brighton Pier, etc., as you will see. And I'll just quote from Drury's description of the bridge, which is a very succinct one, to take us through the way in which the Union Bridge was built. Says Drury, the main chains are 12 in number, arranged in pairs and placed in 3 ranges, one under the other on each side of the bridge, about 1 foot 7 inches apart, and the arrow points to the chain in place. There it is today, with the pairs of chains, one above the other, on each side of the bridge, forming 12 chains in total. There are the chain rods, 15 feet long, 2 inches in diameter. Those are as restored or as newly made during the recent restoration, and as Drury says, formed of the best Welsh iron. Well, they were in 1820, and formed into an eye at each end by welding. The long links are connected together by short open coupling links, 6-inch long centre, 6-inch long centre and centre, made of iron and united to the eyes of the long links by oval bolt pins, which pass through both. That shows you the link itself. The 2 bolt pins, 6 inches apart. There's the pin, one pin, the left-hand pin and the right-hand pin. And I have an example of one of the wrought iron links rejected. Step back sorry, rejected during. Take this as well then. Rejected during the restoration, and the pin, as on the diagram, that fits through the link. Chain bars, says Drury, 15 foot long, and they actually weigh 15 stone, with links, pins and saddle, and the hanger connecting the chains to the decking. There is the hanger leading down from the chains and supporting the decking from the chains. Says Drury, the chains pass through openings in the main pier on the Scottish side. There is the Scottish pier is a freestanding pier, the oldest masonry pier in Scotland. On the English side, the pier is actually built into the cliff behind. But the chains pass through the openings in the main pier on the Scottish side, one above the other, about 2 feet apart, says Drury. The links of the chains are made very short at that part, that they may lie on the rollers without being bent. Well, the chain rods on the top of the Scottish tower were 3 feet in length, just miniature 15 feet ones, reduced to 3 feet in length and weighing 3 stones. And in my talks in the local area, I normally carry a 3-foot rod around with me in the car, but I mean, it proved too much to bring it on the train to you tonight, unfortunately. But there we are. From the points of suspension, the chains pass down 24 feet into the ground and through large iron holding plates, 6 foot by 5 foot. That's in the ground on the Scottish side, about there. And they're kept down by large mound stones and other materials piled up to the level of the road. There's a photograph of my 3 foot, of the friend's 3 foot chain bar with the link and bolt in place. Going back to the previous slide, as I've said, from the points of suspension, the chains pass down 24 feet into the ground, said Drury, and through large iron holding plates. Now, just before the the restoration began, our patron, Professor Paxton's friend in Edinburgh at Heriot-Watt University, Dr. Colin Stove, who is the managing director of ADROC, a survey firm that usually does survey work throughout the world, identifying oil deposits by atomic dielectric survey, rather obviating the need to drill through the Earth's crust to see if there are oil deposits beneath. You simply use this laser survey work, saving a lot of time and trouble. But he came and did a survey of the Scottish anchor plates before the work started, and actually showed the plates at a depth of 7.3 meters below the ground, which was very close to what Drury said when he said they were 24 feet below the ground. Those two anchor plates, this is one of 2 points where I actually encroach into the restoration, with apologies to Simon, were replaced on the Scottish side by an anchor block of about 350 cubic meters. I've said square meters, cubic meters, I think, Simon, poured over the course of 2 days. So that huge anchor block has replaced the iron plates, which are still there. Actually, the contractors, I think, Simon, didn't actually get down as far, didn't get as far as the anchor plates. They're still there under the new concrete, very impressive anchor block. On the English side, says Drury, the chains lie also upon cast iron plates laid into the masonry. The extremities of the chains are fastened, as on the other side, the Scottish side, to large holding plates of the same dimensions. But instead of being sunk deep in the ground, they're placed vertically, rather above the level foundation of the pier, and they bear against a horizontal arch of masonry dovetailed into the rock. So instead of being in the ground behind the tower or the pier, as on the Scottish side, they're actually back into the rock above the pier on the English side. And so everything went happily until 1902, when the then surveyor of the Tweed Bridges Trust, who'd taken over from the Turnpike Trust, took fright at the security and integrity of the bridge, and recommended to the trustees of the Turnpike Trust that it ought to be strengthened with, in his words, Joseph Bean's words, new and additional steel wire cables, the practical effect of which would be to strengthen the bridge to such a degree as to provide an equivalent to a new bridge, because that was one of the options that the trustees had to consider, whether to abandon the suspension bridge or the suspension bridge of 1820 and build a new one at colossal cost. But the cost of the proposed improvement, the addition of these wire ropes on both sides of the carriageway, would be approximately £1,450, very much cheaper than building a new bridge. And the trustees agreed to that and installed the wire rope, as you see there, with additional hangers supporting the decking. And as Simon will no doubt tell you, the preparatory to the restoration of 2020, it was found that the 1902 rope was doing more harm than good, and it was decided not to replace it. And there we have the second of the two slides of the restoration, for which I apologize to Simon. There's the wire rope meeting an ignominious end on the decking of the bridge in 2021, removed from the chains, and it was cut up and not replaced. Let's just go back to what is, I think, or what we believe is the earliest known photograph of the bridge in the middle of the 19th century, with its original decking, a chap taking his ease on the downstream footpath, a horse and cart, just about to enter the bridge from the English side, and there is the toll house keeper, Edward Roxburgh, and his family standing in front of the toll cottage, two-roomed cottage, under the portico. And you'll see the arrow pointing to some sort of emblem just above the parapet of the bridge, which is actually an entwined rose and thistle device above the maxim, "United strength is stronger," as they said in 1820 and have continued to say over the decades, and that plaque on the English side, and another one, an identical one on the Scottish tower, they were restored during the restoration works. The English plaque came down and was restored off-site, and from it was taken this computer-generated 3D print showing what you can't really see when you look up at the plaques from underneath, from below the bridge, from below the tower, hands clasped in friendship, obviously across the border. And the significance of that is that the original location of these plaques was in the very center of the bridge, attached to the chain rods in the center, and there are holes in the back of the box underneath the emblem, where the chain rods would pass through. Why they were removed from the middle of the bridge, nobody really knows, but they were relocated on the top of the two towers, and the English one came off for restoration. The Scottish one steadfastly refused to budge, I understand, and had to be restored in situ on the Scottish tower. Just continuing the timeline, in 1837 there were substantial repairs to the platform itself, and then in 1871 it was redesigned and completely replaced. In 1883, when turnpike tolls were abolished throughout the country, the Tweed Bridges Trust, a body comprising trustees appointed from both sides of the border, was formed, and the Tweed Bridges Trust precepted on the local authorities for the cost of maintaining the Union Bridge, along with the other two bridges, the traditional masonry bridges, that actually cross the River Tweed at the border of England and Scotland, Norham Bridge and Coldstream Bridge. And in terms of the maintenance, the day-to-day maintenance and responsibilities of the bridge, I think Northumberland County Council drew what perhaps they would regard as a short straw, in that they got the Union Bridge and all that entails in terms of maintenance, while Borders Regional Council, and Scottish Borders Council as now is, have responsibility for Norham Bridge and Coldstream Bridge, I think. But both authorities are 50-50 responsible for the costs of maintenance. The toll cottage that you saw in the picture was condemned in 1934 and demolished in 1953. And the pier of the English tower was refaced with the facade of the portico of the toll cottage pushed back and into the face of the pier. In 1974, there was a complete platform replacement, and the suspension chains and the Scottish Tower bearings were overhauled. And in 1986, somewhat controversially, the Tweed Bridges Trust was wound up, and responsibility for the bridge passed to the two local authorities, the two riparian local authorities, as I've said, Northumberland and Scottish Borders Council, but also influenced, because it's a cross-border bridge, by Historic England and Historic Scotland, Natural England and SEPA, etc., and all these agencies had to come together, along with the maritime agencies, as Simon would perhaps tell you, in 2020, to authorise the works on the bridge, and even to the extent of the lottery funding. It was a new venture as far as the lottery funding was concerned, because they had to deal with an application that covered the restoration of a property in the two nations. So it was altogether a unique experience for all these agencies. Just digressing again slightly, the same Dr. Stove that I mentioned in terms of the radar survey of the Scottish plates, carried out an analysis of two links first of all from 1820 and secondly from 1974, and produced these graphs, which I can't explain other than showing you them. And even our patron, Professor Roland Paxton, who at the opening of the reopening of the bridge in July 2023 was described by one of his colleagues as, at the age of 93, the David Attenborough of civil engineering. Even Professor Paxton didn't understand what was being described to him in looking at these graphs. But you'll see that the 1820 link sample produces a very different graph from the 1974 link sample, and the suggested reason for that is that the amplitude of the transmissions is much stronger in the 1820 sample than in the 1974 sample, with 8 octaves of sonification in the former as against only 5 octaves in the latter. And could the loss of signal transmission be due, says Dr. Stove, to stretching of the link, or possibly stress or strain? Well, that's as may be, and it makes an interesting pattern, an interesting picture. But I'm afraid I can go no further than that. What is much more understandable, as far as I'm concerned, is, and you're going to show that one. Sorry. Well, anyway, sorry. This is as far as I'm concerned, it's a marvelous, graph showing the 24 layers of paint and I'm embarrassed now because Simon's going to tell you about this as well. But from 1820 through to the present day, starting with a scheme in 1820 which lasted for 2 years, when the bridge was painted black all over, and the suggestion was that it was painted black in mourning for the death of George III at that time. But you'll see there an advertisement for the repainting of the bridge 2 years later in a colour scheme that just about matches, I think, the present colour scheme of the bridge. When I came to the Union Bridge in about 1977, we were up to schemes 21 and 22, when the bridge was painted in white or a very light grey all over. And I have to say that it was I found that a marvellous colour scheme, because on an autumn morning, a cold autumn morning, with the mist rising from the River Tweed through the chains of the bridge, it really did present a quite ethereal image, which you know, was quite attractive. But what we have now is I think, as Simon will confirm, the more or less the original colour scheme after the first 2 years of an all black drab structure. That takes us on to where I actually stop, apart from one or two little interesting snippets. The ACOM Conservation Management Plan of 2010, from which stemmed the restoration works of 2020 to 2023, which Simon is going to tell you about. Just one or two possibly interesting little side issues. This is the International Historic Civil Engineering Landmark Award, which is affixed to a plinth on the Scottish side of the bridge, promoted by our patron, Professor Paxton, but sponsored by the American Society of Civil Engineers and the Japanese Society of Civil Engineers, along with our own ICE. It's in very good company in that Sydney Harbour Bridge, the Thames Barrier, and significant engineering works like that have been granted this prestigious award. And so we are delighted that the bridge has it. And it was presented, of course, to the two councils, to Northumberland County Council and to Scottish Borders Council, by the three organisations. It was dedicated on the 26th of July 2020, but COVID intervened and meant that it couldn't actually be unveiled until significantly later. And there we have the unveiling ceremony with, from the left, the ICE representative, Professor Paxton, the David Attenborough of civil engineering, a remarkable patron who's done a terrific amount for not only the Friends, but the bridge in general. The Japanese representative, and nearest to the camera, the American Society of Civil Engineers representative. That was a remarkable ceremony. And another remarkable ceremony was on the opening, the formal reopening of the bridge, the rededication of the bridge by representatives of the Church of Scotland in the foreground. On this side of the new stainless steel borderline that is shown in the bridge. It's the topographical border between England and Scotland, not exactly in the centre of the bridge, but the Scottish minister on the English side with the bagpiper, the Canon Kelsey of Norham on the English side, with a Northumbrian piper hidden somewhere. And it was a very poignant ceremony, and that's our chair at the time, Martha Andrews, casting onto the waters of the River Tweed a wreath comprising English roses, Scottish thistles, and somewhere in there is a leek as well, to symbolise the involvement of the three nations in the building of the bridge. And finally, another prestigious award, the National Transport Trust Red Wheel Award, which was presented to the bridge last year in recognition of the significance of the Union Chain Bridge. I shall leave it at that and hand over to Simon, who's going to tell you about the restoration itself.
Thank you, Ted. There is a lot to cover regarding the restoration, so a lot of it's going to be heavily abridged. Fortunately, Ted's thrown a couple of nuggets in there, which saves me having to explain some things. I want to concentrate on one particular aspect, but I'm happy to answer any questions at the end. This all started in the late 1990s when we started to get hanger failures. Some of the shorter one hanger snapped. It was replaced with a temporary repair, but as time went on, we got another one and then another one, and the time period between each fracture was getting shorter. Every time we went to fix the bridge, we had to get listed building consent, and I think after a number of times, I think they got a bit fed up with what we're doing and insisted that we wrote a conservation management plan, which is what Ted referred to. This really marked the start of the serious efforts in trying to figure out how we were going to restore the bridge. It spelled out in great detail what the current state was, what needed to be done, and what invariably would happen if we did nothing. Northumberland County Council has its own internal capability. So over a 4-year period, we designed and brought together a restoration scheme, working very closely with Historic England. We also spent quite a lot of time working out how we were going to fund this. We did have an original abortive attempt at National Lottery Heritage funding, but after a couple of years we went back with a different outlook, and through 2 rounds of bidding we're successful in getting the £3.1 million award. And that effectively became the seed funding that then convinced Northumberland County Council and Scottish Borders Council to contribute the remaining costs of roughly £6 million. The contract was awarded in June 2020 and works commenced on site in August of that year. As Ted mentioned, there had been previous refurbishments, a rather alarming photograph there of showing them replacing the decking. And interestingly, in the 1974 refurbishment that Ted referred to, they did replace a number of corroded links and pins with a rather ingenious chain detensioning device, which allowed them to do these works in situ on one chain at a time. And we'll see later on why it possibly wasn't the best way of doing it. And you can see that is the condition of some of the elements in 1974. We decided for our refurbishment that if this bridge was going to last for another 200 years at least, then the only real way of doing it was to dismantle it completely, look at every component, repair and replace as necessary. It seems quite a daunting task, but the bridge is actually quite a simple structure. The difficulty is figuring out how you're actually going to do that. So in that photograph, you can see we have an aerial ropeway with an underslung platform, and that's what provided the access for the works. So starting from the English end, we dismantled one bay at a time, one bay being 3 hangars and the associated deck. You can see the access gantry suspended off catenary wires. There's 2 smaller individual man gantries as well, plus a cable crane, which traditionally those are used in the logging industry to hold trees off mountainsides, but in this instance it was used to carry the removed components back to the land. And you can see there a bit more detail of the guys actually dismantling. By this point, you know, that the wire rope had gone. The beauty of the access was it didn't really matter to us what the river did. Other options included having jack-up barges in the river. There was quite a significant flood at one point, but we were carried on working unhindered. Obviously, once you've taken all the deck off, the next thing is to dismantle the chains. This was done by supporting the chain on the catenary wire with pulleys and strops. If you tension the catenary wire, it picks the chain up, it allows it to be disconnected and then basically just hauled in. You can see there's a smaller cable there. All the pulleys are connected with a hauling rope, and there's a pulling winch at one end and a braking winch at the other. So basically just like drawing a set of curtains, just pull it back, take off 1 bar at a time, repeat that. Obviously, how do you get the pulleys and strops on? Well, guys have got to walk out on the chains to connect them. There is no other way of doing it. They are harnessed on. You've done it once, just repeat it 11 more times and you end up with no superstructure. It's gone completely. All that's left, excuse me, are the temporary catenary wires, and you can see the cofferdam excavation for the anchor block that Ted referred to. The planned works for this refurbishment scheme, replacement of the chain anchorages, this could be an entire talk in itself. So a new mass anchor at the Scottish end and new drilled rock anchors at the English end. Replacement of the timber deck, I forget how many times it's been replaced in the last 200 years, but it hadn't, I probably don't think it had been touched since the 70s, so it was quite rotten. Obviously, there were quite a few masonry repairs and replacement to do. The local sandstone is quite soft and quite variable in quality and can weather quite badly. As Ted, well, 1902, 1903, I think is when it was starting, when it was finished. We found in the analysis that the wire rope took less than 1% of the live load on the bridge, and that's fundamentally the difference between a solid iron bar and a wound wire rope. Completely different stiffnesses. It took no load. It made the original structure slightly indeterminate, and it caused a lot of damage because it wasn't a lot of tension in it, and it would sway from side to side, and its hangers would damage the chain bars. So that was removed. We had the refurbishment and repair of all the wrought iron hand railing, and perhaps the most problematic element, and the thing that I do want to concentrate on, is the refurbishment, repair and replacement of the chain components, something that referred to as component retention, and it did cause us quite a few issues. Excuse me. As Ted was describing earlier, fundamentally there are 6 pairs of chains. The chains are connected together with links in black, pins, a gib key and a washer to stop the pin coming out from the links. 2 pairs of chains form a knuckle upon which sits a hanger cap, which the hanger sits in and is locked in place by a wedge. In the 1974 refurbishment, they mainly concentrated on links. They replaced 744 pins with the associated gib keys and washers. And they also replaced 422 of the links. So there you can see the remaining original components after that refurbishment. The replacement components were all spheroidal graphite cast iron as opposed to wrought iron. I was thought to be the most appropriate material at the time. So what we're going to go through is look at what we did in the 2023 refurbishment. As part of the listed building consent, we had to put forward, working with Historic England, an estimate of the number of components that we expected would need to be replaced as part of the consent process. And we'll go through all these one by one. The hangers were problematical because it started to break, and we were trying to understand why. The ones that had broken, the hanger cap was put into storage, and there was a simple stainless steel threaded bar and flat plate put in its place. We thought the problem was because the hangers are only 1 inch in diameter. Where they fit into the hanger cap, they're actually locked solid with the fishtail and the wedge. They can't move, they can't rotate. The bridge is very lively and the deck does move relative to the chain. And we thought, having looked at the failure pattern where they had broke, it looked like it was a fatigue effect. So we put some small strain gauges on some hangers, drove cars up and down it and measured the stress. What's interesting there is a significant fatigue in stress. The axis on the bottom is in seconds. So you can see from there, the car was off the bridge at 22 seconds, but there was still a fatiguing effect nearly a minute later. We use this information to do some sort of back calculation of fatigue damage over 200 years. And it did appear to conclude that there was this inherent fatigue defect in the original design, which Samuel Brown would have known nothing about at the time. So the problem was how to replace it. We looked at all different things, but nothing could replace that original detail. So the brute force approach was, in discussions with Historic England, was to replace all the hangers with hangers made from high yield steel, which is sufficiently fatigue resistant not to succumb to that effect in the future. You'll notice some strange ends on those bars we call the fishtails. We decided to make that a slightly better detail. The original hangers just had what we call a fishtail, which is a one-sided wedge, and then a secondary wedge that is hammered in to lock those into place. All the hanger caps are different sizes. All the fishtails are different sizes. They don't all fit together properly. They've been hammered in quite extremely, and we'll see that caused other problems later on. So we decided to have what we call the dovetail wedge. That wedge locks in, so the hanger can be pushed up from below through the cap, the wedge put in, and then the hanger falls down. You don't need to hammer that into place because it's now too big to fall through the hole in the pocket. And it's actually got, as you can see on there, slightly curved outer faces, which enables us to rotate it to suit the angle of the chain going up as it gets steeper. The original hangers had been bent literally in situ, sometimes one way and then the other when it was too much, and that in itself would have compounded the fatiguing issue. And these were all, again, all high yield steel that was welded on the end of a 1-inch rod. So obviously that was agreed in the listed building consent to replace all 146, and it meant that there were now no originals remaining. Looked at washers next. You'll see there were only 64 original washers left. They unfortunately had succumbed to corrosion. The pins and washers that weren't attended to in the 1974 refurbishment were generally up towards the higher end, towards the Scottish Tower. Now, whether it just access was too difficult to get up there, I don't know, but that's generally where all those components were concentrated. So they were replaced with, again, high yield steel, laser cut from flat plate. We found throughout the whole process of dismantling, there was a lot of variation in component size because all these things were effectively handmade. So we took the decision to have varying thicknesses of washers made to allow us to make it easy to get things put back together when it came to reassembly. So in the listed building consent, we'd estimated we might have to replace 584 washers, but we actually replaced slightly less. But again, no original components were retained. Same goes for gib keys. Of the 64 original gib keys left after 1974, they either were fused into the link and couldn't be removed, which you can just see at the far end there, or they broke when they were being removed due to excessive corrosion. They were quite a simple element that was just laser cut from flat steel plate. Only 203 of those were replaced. A lot of the 1974 ones were reusable. Again, with the pins, only 64 original ones. That was a pin recovered from the top of the Scottish Tower. There's not a lot we can do with that, fortunately. And one of the problems with wrought iron is there aren't really any repair techniques available for structural components like that. Unfortunately, quite a few of the 1974 spheroidal graphite pins had cracks and casting defects in them, which meant they had to be replaced as well. The pins were quite unique, as I think Ted mentioned. They were oval in shape, in a sort of round link, which just concentrates the bearing pressure. They were all CNC machined out of billet steel, quickest, most accurate way of making them. We'd consented 100, we replaced 103. So all the original 64 plus a few of the 1974 ones. The links are a little bit more interesting. After 1974, there were still 362 original links. Oh, Ted's taking them back. There we go. It's one of the original wrought iron links. When we started to look at these, once they were all blasted clean, you can see quite a lot of section loss on virtually every wrought iron original link. Because these were original components, and we wanted to try and keep as much original stuff as possible, we did some quite complex finite element analysis to try and understand what the absolute minimum cross-sectional area of metal was that we could get away with in the design. Unfortunately, there wasn't enough material left in any of the original links that had to be replaced. Unfortunately, in some of the 1974 spheroidal graphite links, we found heavy porosity and some had cracking on the pin bearing surface, so we had to replace all of these. They're again quite simple parts to make, laser cut from plate and hand finished. So of the 362 original links, they were all replaced, plus about a quarter of the ones from the 1974 refurbishment. Chain rods. When we blasted all the paints and various other items off the chain rods, we found the main shafts themselves were fine, but all the eye ends had different degrees of corrosion. Some were quite severe. Some were wondered, actually what residual capacity was left in the bridge, what factor of safety it was operating at. Again, being original items, we wanted to try and retain as many as possible. So again, we used finite element analysis to understand what was the minimum cross-sectional area we could get away with. And we'd spent, well, I made Ryan do most of it, Ted, but a lot of time measuring all the eye ends of all the rods. And there's the results. What we found, generally, there's a 25% variance in size of the rod ends, because they're all handmade, they're all hand forged. And the bottom is the uncorroded section, and the vertical axis is the corroded section. So you can see how many actually failed. What was interesting is you could have, because there was a 25% range of sizes, you could have one that looked very corroded, but there was enough metal in there because it was a big one to start with. Whereas you had some that had no corrosion at all, hardly, but were that small that it didn't take much to fail them. So, and interestingly, I think, was that say on there? It was only 52% of the eye ends failed, but there's one on each end of a rod. So it meant that overall 70-odd% of the rods couldn't be reused. So the next conundrum was, well, how are we actually going to replace them? And the fact that they varied in size by 25%. So bang up to date, we decided to make some mock-ups, 3D printing them, and then look at actually trying to assemble them with the existing components that we had until we determined on what was a reasonable average sized eye end to have, because we weren't going to make a load of unique ones again. That 3D printed model was used to make an extremely expensive machine tool, and the replacement eye ends were upset forged from blanks. Quite a lot of them. These were put into jigs to be welded onto the plain round bars. As you can imagine, that's quite a critical weld of a component that's purely in tension. I think you can see from the guards around the weld there that the whole concept of the welding was to avoid having stop starts within the weld itself. So there's a lot of additional weld material. That's after the guards have been cut off, that all had to be sort of flattened down. That's the rods after they've been linished. That's after they've been MPI'd and before they went for X-ray. Every weld was X-rayed. Initially, quite a lot of them failed. They had to do some improvements to the welding techniques. And ultimately, we ended up with managing to retain 110 of the original rods. 282 had to be replaced, but we kept 110. They all went back in the place that they came from. So although we got lots of new rods, everything was tagged. We knew every single component where its original location was. So the original ones we put back in the same place. It might not have been 110 because during the inspections for the works, we did some magnetic particle testing on the chain rods in situ, and you can just make out highlighted in yellow, there seemed to be a bit of a crack. And that appeared to be in the vast majority of chain rods. So we knew that was going to be an issue to look at. When we got them down and blasted, you can see probably 3/4 of the rods exhibited what appeared to be that crack. You would think a critical location. But because so many rods were like that, our view was it was probably a characteristic as opposed to a defect. And thinking about how these were made, I know so Ted mentioned in the quote about them being welded. They were forge welded, which is effectively battering two pieces of nearly molten metal together and fusing them. So you can see this one would have been made by wrapping the link round in that direction back up to meet the bar. And we thought that the very edges of that bar would cool down so quickly, because the body of the bar would retain the heat, but the edges would cool that quickly that there wouldn't be enough heat for them to fuse. So what we did was we took a number of the chain rods that were going to be rejected because of corrosion, took them away, sliced them up and examined them. So that one in particular there, once you cut it open and examine it, there is no defect inside. It is just a surface defect from the very edge, just cooling and not fusing. You can see it's all fused in there. You can actually see in that some of the laminar nature of wrought iron. So that meant every time we saw that, what appeared to be a crack, it was okay. It was just a characteristic of the way it was made, and it was perfectly acceptable to retain those rods into the works. So that's how we managed to maximize the original ones. Hanger caps, 146 of those. They're quite a unique part of the structure as well. They'd been up there for 200 years, covered in 24 coats of paint. Nobody really looked at them. So when we took them down and blasted them, much to our disappointment, we found that nearly all of them had cracks in the corners of the hanger pockets. Most of them had at least one. Many had two. Quite a lot had three, and some had 4 cracks, one in each corner. Clearly, replacing all those was not something we really wanted to contemplate. So we're looking at, there's a little diagram of how the wedge fits in there. The cracked in the top corners, we're thinking, well, if that track tries to work its way down, the actual element gets thicker, so there must be a point at which it comes to a balance. We're trying to understand, why was it cracked? Has it cracked in service? Are they getting worse? Did it happen initially? So what we thought we would do is to test them. So we took some of the hanger caps that were badly cracked and some that were going to be rejected for other reasons. And we set up a little test rig in a container where we could shut the door and monitor it with a camera just in case. We fitted incredibly precise strain gauges to these in each of the corners, and then had an arrangement where we pushed the fishtail in, used 2 half wedges just so we could centralize the load. And we had 4 loading regimes going up to 5 times the maximum sort of working load in each time, going up in increments and seeing what happened. So this was one of the caps that was tested at 2.5 times working load. You can see, we've got a pointer. Doesn't matter. So you can see that the strain strain across the bottom, load up the side. You can see that initially strain increases linearly with increasing load. The little steps in the graph line are purely because of the sensitivity of the strain gauges. When we get to 2.5 times working load, we unload it. The strain really doesn't change because at this point, the wedge is locked in. When we release it, it goes virtually all the way back. 0.4 microns is not really a significant measurement. So that just shows that everything behaves elastically. So the crack grows a little bit, just goes back where it was. When we repeat the same tests, but going up to five times working load, you can see that initially it's a linear relationship, then it goes non-linear, then there's kind of a bit of an immediate settlement, and then once we finish, there's a permanent residual strain that tends to indicate crack propagation. So those cracks were starting to get bigger under that loading regime. So this testing allowed us to understand what was going on and determine that under the normal range of loading, those cracks were not going to propagate, which meant we could retain the hanger caps. We concluded that the cracking had been caused by them hammering the wedges in. Like I say, all the hanger caps would have been cast in molds, but all those pockets were different sizes. All the wedges were different sizes. The fishtails were different sizes. There was no lead packing or anything like that to distribute load. So these things had to be hammered in, because if you didn't hammer the wedge in, the hanger could actually pull out, which is why we designed ours to be slightly differently, that you didn't have to hammer them in. So the only conclusion we could come to was that the physical distress that had been subjected to initially when it was built to ensure the hanger wouldn't fall out was what caused the cracking. There were a handful of caps that had to be rejected for various reasons. One, you could stick an entire biro in some of those holes and it just disappeared, and that's the main wing that supports the cap. And there were a couple that were just incredibly poor castings to start with. The new ones were again CNC machined from a 3D model. That was quite a complex process. And again, we had to come up with an average sized cap. They were all different sizes, but we had to determine what would be a nice average size to fit every location. And that meant that we only rejected, we thought we might have to replace 5. In the end, we only replaced 8, so we managed to keep 138 of the original caps. Which brings us on to this whole question of originality. I mean, Ted alluded to the number of times the deck had already been changed before 1974. And we had worked very closely with Historic England all the way through this. And at the end, when we finished and presented the report on all the retention issues for components, this is what they had to say. You know, the principle of repairing the Union Chain Bridge has accepted from the start of the project and through its planning permissions the need to retain the structure as the world's oldest chain link bridge still used for vehicles. It follows that its components need to meet modern structural and material standards. And they also said that they considered that the degree of proposed replacement was justified, that some of the wrought iron components had already lasted 150 to 200 years is a testament to their manufacture and the design concept. But the analysis shows the degree to which the majority have reached the end of their working life. Replacement of its chain link structure is an inherent factor with this type of bridge, and replicas in modern materials can be accurately detailed to ensure that the bridge both functions and appears as originally designed. And that's the key thing, it functions and appears as originally designed. What Historic England what they wanted was people to enjoy the bridge as an entity, as opposed to an original preserved item that you wouldn't be able to use. You know, we were heading towards the bridge being pedestrianised and then ultimately closed, but we've ended up with something that people can use freely. One of the reasons we did 2 principal inspections, yet we still, you know, from what I've talked about, you would think that we'd got a little bit caught out. And to be honest, we did with the condition of some of the components. Ted's already stole me thunder and thrown that slide, but A lot of the components had never been blasted. They'd just been repainted over and over again. So there was quite a thickness of paint that masked a lot of things. We also disappointingly found that in the 1974 refurbishment, when things were reassembled, a lot of flexible filler had been applied to corroded pins, painted over, and these were then hidden behind the links. If we'd known to look for it, we might have looked a bit closer, but we didn't. And there was nothing in the records for that scheme.
Was that Bowman's egg?
Bowman's egg?
The filler. That was the filler that failed on the bridge at Dundee over the time.
No. So, yeah, maybe we could have done more inspection at the time. But no matter how much inspection we did, you would still have to dismantle everything to be sure that you could get your minimum 120 year, another 200 year design life out of it. So fortunately, we did dismantle it and not try to do things in situ. So the reconstruction. Did anybody try to fix their own car years ago using a Haynes manual? Yeah? You remember that, wouldn't you? Yeah. Never a true word was spoken. So having pulled all the chains off the bridge, we need to pull them back out, simply reversing the process. So they were hauled back out on the catenary. The catenary's held high with tension in it until the chain's in place. The pins are put in to connect it. Then the catenary's slackened off and the chain drops into place. Do that 12 times, you've got a set of chains. The replacement chains inside the English tower had a McAloy spade end on them, so we could actually adjust the length to trim them all to get them all at the same height. With the chains in place, it's back to hangers, timber, cross girders. You can see the longitudinal stringer and bowstrings that help to support the deck timbers. Again, working back towards England. You can see that's the gantry in use there. Once it's nearly done, once all the timber decking's on, the framework start to we put the timber deck back as originally as possible. Yeah, so timber BT ducts, they're not original. We did depart, when we came to do the restoration, there were Acme panels on the road decking, and we've replaced them with, it looks identically the same, but they're actually GRP, so should last a lot longer. Footways on, nearly completed. All that was left was to dismantle the temporary works. As we said, it said all of those that worked on the bridge, there's one thing that's remarkable for us. One day there was a bridge, and then there was nothing, and then we put it back.